I'm Donna Arnold at the University of Kent, and I investigate new materials. Magnetic materials can be considered to be made up of a series of bar magnets which are randomly orientated. When we apply a magnetic field, we can align these bar magnets, or magnetic moments as they are known, in the same direction. This is known as ferromagnetism. Similarly, in some materials we can have a distribution of positive and negative charges. This distribution of charge is known as a dipole moment. Like magnetic materials, we can align this dipole moment in the same direction by using an electric instead of a magnetic field. This is known as ferroelectricity. In both cases, this means that when we apply a magnetic or electric field, we can align either our magnetic moments or our electric dipoles in a single direction, for example, all pointing up. We can think of this as a one or an on state. If we now switch the direction of the field, we can align either our magnetic moments or electric dipoles in the opposite direction, or all pointing down. We can think of this as a zero or an off state. This means that we effectively have a way to store data as a series of zeros and ones, known as binary code. We can exploit this in lots of applications such as data storage and memory in computers and games consoles. Ferroelectric materials also have a whole host of other potential applications, such as in fire sensors, medical ultrasound instruments, infrared cameras, sonar, and vibration sensors. Some materials, however, may contain lead, which is toxic as well as being bad for the environment. This means when designing new materials, it's important to ensure they are lead-free. We use Diamond Light Source, the UK's national synchrotron science facility in Oxfordshire, which is a particle accelerator similar to the Large Hadron Collider at CERN in Switzerland, to investigate our materials. Electrons are fired into the small ring from an electron gun and accelerated using particle accelerators to speed the electrons up so that they are travelling near the speed of light. The electron beam then travels round the larger storage ring. However, in order to be able to travel round the ring, the path of the electron beam needs to be bent, and this is done using a series of magnets. Every time the path of the electron beam is bent, the electrons lose some energy, which is given off in the form of light. This light is then directed down channels to 24 different areas where scientists use it to conduct experiments. We use this light to investigate the structure of materials so that we can understand the effect of the structure on the magnetic and electric properties. Ultimately, we hope to design new multifunctional materials which have both ferroelectric and ferromagnetic properties. These materials will form the next generation of lead-free devices which operate faster and more efficiently, at the same time as consuming less power and offering lower costs.